dark matter. Physicists have been chasing it for nearly a century and still cannot tell you what it is. In the 1930s, astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving far too fast. The visible mass couldn't explain it. Something invisible was holding everything together. Scientists now believe dark matter makes up roughly 27% of the universe. It doesn't emit light. It doesn't absorb light. It passes through ordinary matter like a ghost through a wall. Detectors buried deep underground have been listening for it for decades. Nothing confirmed. The machine that built the universe runs on something we cannot see and cannot name. Fast radio bursts. 1 millisecond. That's how long a single fast radio burst lasts. In that blink, it releases more energy than the sun emits in 3 days. The first one was discovered in 2007, buried inside archive telescope data from 2001. Nobody expected it. Then more appeared. Then one repeated, which changed everything. Because repeating signals suggest a source that survives. Most are traced back to distant galaxies, billions of light years away. Some repeat on eerily regular schedules. Magnetars are the leading suspect, but the precision of certain bursts doesn't fit neatly. The pattern feels almost deliberate. Scientists are careful not to say that out loud. The cosmic web's missing baryons. Run the numbers on ordinary matter in the universe and you hit a wall. About half of it simply isn't where the models say it should be. This is called the missing baryon problem. For decades, cosmologists assumed the math was wrong or the instruments were too weak. Then in 2017 and 2018, 2 independent teams finally detected the missing matter hiding in enormous filaments of warm gas stretching between galaxies. Problem solved, right? Not quite. The distribution still doesn't fully match predictions. The web exists. Why it's structured the way it is remains genuinely open. The Hubble tension. 2 different methods for measuring how fast the universe is expanding keep producing 2 different answers. Both methods are precise. Both teams are careful. The gap between the numbers is too large to be a measurement error. One method uses the cosmic microwave background, the afterglow of the Big Bang. The other uses nearby supernovae and distance ladders. The results disagree by roughly 8%. That sounds small. In cosmology, it's a crisis. Either one method is fundamentally flawed, or the standard model of cosmology is missing something real. Physicists call this the Hubble tension. Some call it the first crack in the foundation, the asymmetry of matter and antimatter. When the universe was born, matter and antimatter should have been created in perfectly equal amounts. They should have annihilated each other instantly. Nothing should exist. And yet here you are. Something tipped the scale. A tiny excess of matter survived, 1 extra particle for every billion annihilations. That survivor is everything you see. The process that caused this imbalance is called baryogenesis, and no confirmed physical mechanism has been found to explain it. The standard model predicts a tiny asymmetry, but nowhere near enough. The universe exists because of an anomaly that current physics cannot fully account for. The Lithium Problem. The Big Bang nucleosynthesis model is one of physics' great successes. It correctly predicts the abundance of hydrogen, helium, and deuterium in the early universe. Then you check lithium-7. The universe contains about 3 times more of it than the model says it should. That discrepancy has survived decades of scrutiny. New stellar physics has been proposed. New nuclear reaction rates have been tested. Nothing closes the gap. It's not dramatic enough to make headlines, but cosmologists know it's there. A quiet, stubborn number that refuses to fit. Some researchers believe it's pointing at physics beyond the standard model. Others aren't sure. Where to look? The void of the universe. Scattered across the cosmos are enormous regions containing almost nothing. No galaxies, no dark matter filaments. Just emptiness hundreds of millions of light years across. The largest known void, the Boötes void, spans roughly 330 million light-years. It was discovered in 1981 and immediately unsettled astronomers. In a universe that should be roughly homogeneous on large scales, a hole that size shouldn't exist. Models of cosmic structure formation struggle to produce voids this extreme. What drained them? How did matter evacuate so completely? The leading theories involve early universe density fluctuations, but none fully explain the scale of what's been observed. The black hole information paradox. Drop a book into a black hole. According to general relativity, it's gone. According to quantum mechanics, information cannot be destroyed. These two pillars of modern physics directly contradict each other at the event horizon. Stephen Hawking proposed in 1974 that black holes slowly evaporate through radiation, but that radiation appears to carry no information about what fell in. So where does it go? Hawking spent decades wrestling with this. Before his death, he suggested information might be stored on the event horizon's surface. Others propose firewalls, fuzzballs, or entirely new geometry. No consensus exists. The paradox is still open, and it may require rewriting physics at its deepest level. The Pioneer Anomaly. NASA launched Pioneer 10 in 1972 and Pioneer 11 in 1973. Both probes sailed out of the solar system on precise trajectories. Decades later, scientists noticed both were drifting slightly off course, not randomly. Both were being pulled back toward the sun by a tiny, unexplained force. For years, this was called the Pioneer Anomaly and generated serious speculation about unknown physics. Then in 2012, a detailed thermal analysis showed that asymmetric heat radiation from the probes themselves was creating the drag. Case closed. But the episode exposed something important. Even our most precise models of spacecraft dynamics had a blind spot. The universe finds the gap every time. The cosmic cold spot. In 2004, astronomers mapping the cosmic microwave background found something that shouldn't be there. A region of the sky, roughly 1.8 billion light-years across, that is measurably colder than everything around it. Far colder than statistical variation allows. It's called the CMB cold spot. One explanation is a supervoid, an enormous region of low-density space that drains energy from photons passing through it. A candidate supervoid was identified in 2015. But its size and depth don't fully account for the temperature drop. Another explanation, proposed seriously by some physicists, is that it's a bruise left by a collision with a parallel universe. That idea is not confirmed. It has also not been ruled out. Quantum entanglement and non-locality. Two particles become entangled. Measure one and the other responds instantly, regardless of the distance between them. Einstein called this spooky action at a distance and spent years trying to prove it was an illusion caused by hidden variables. In 1964, physicist John Bell designed a test. Experiments beginning in the 1970s and refined through 2022's Nobel Prize-winning work confirmed it. The spookiness is real. Entanglement is not a trick. But here is what nobody can explain. How does the information travel? Nothing moves between the particles. No signal is sent. The correlation simply exists across space. Quantum mechanics predicts it perfectly. It cannot tell you why. The origin of cosmic rays. Every second, high-energy particles rain down on Earth from deep space. Some carry energy so extreme they should not exist. Above a certain energy threshold called the GZK limit, particles traveling through the universe should lose energy by colliding with background radiation and degrade before reaching us. Yet, ultra-high-energy cosmic rays arrive anyway. Some appear to come from directions with no obvious powerful source nearby. The Pierre Auger Observatory has been tracking them since 2004. Candidate sources include active galactic nuclei and gamma-ray bursts. But the origin of the most energetic events remains unconfirmed. Something out there is accelerating particles to energies our best accelerators cannot touch. Every one of these mysteries shares the same uncomfortable structure, a model that works brilliantly until it doesn't, a number that refuses to fit, a signal that arrives from nowhere.